acid halides as derivatives of carboxylic acids undergo nucleophilic acyl substitution reactions. Now, we have seen before that they are actually the most reactive carboxylic acid derivatives. That's because of course, the inductive effect, resonance effect, which makes carbon of acid chlorides, for example, as a typical example of an acid halide, the most electrophilic, and also the leaving group ability. The chloride ion was the best leaving group amongst the other possible leaving groups, as for example, acid anhydrides like the carboxylate ion in acid anhydrides, the alkoxide in esters, or the amide ion in amides. So the chloride ion or halides are actually better leaving groups in general. They are the best leaving groups in general amongst carboxylic acid derivatives. So that's exactly why they are the most reactive. Let's draw a general structure for an acid chloride as a typical example, if you like, of an acid halide. So this is general structure of an acid chloride. So since acid chlorides are the most reactive, if you like, amongst carboxylic acid derivatives, therefore acid chlorides can be transformed into all other carboxylic acid derivatives which are less reactive, as we have seen before. And remember, we talked about nucleophilicity and leaving group ability. So acid chlorides can therefore be transformed into acid anhydrides. And that's, of course, if we react the acid chloride with a carboxylate ion. So this is the general structure of an acid anhydride. That's an acid anhydride. This is an acid chloride. This transformation is possible if the acid chloride is treated with a carboxylate ion. Remember, you need this unit to attack this carbon in nucleophilic acyl substitution reaction, of course, with departure of the chloride ion. So the carboxylate, therefore, is required to form an acid anhydride from acid chlorides. So that's one important reaction, transforming acid chlorides into acid anhydrides by treating the acid chloride with a carboxylate ion. And of course, if you remember, these carboxylate ions are actually conjugate bases of carboxylic acids, which can be made, therefore, from the corresponding carboxylic acids by treating the carboxylic acid with a mild base, such as only or sufficiently the hydroxide ion or even sodium bicarbonate. So that's one reaction of acid chlorides. The other reaction, obviously, is making esters from acid chlorides, and that's, of course, if you react the acid chloride with an alcohol, ROH. So we need OR. So ROH would be the source of OR, and a mild base is also required, such as pyridine. We will see a possible mechanism for this reaction. So if you treat an acid chloride with an alcohol in the presence of a mild base, the corresponding ester will form. This is a very useful transformation. Of course, it's very widely used to make esters from acid chlorides. And remember, so this is an ester, this is an acid anhydride. So remember, esters can be made also from carboxylic by direct transformation of carboxylic acids into esters, of course, using the two methods, the Fischer esterification, as we have learned before, or also by treating the carboxylic acid initially with a base and subsequently reacting the carboxylate ion with an alkyl halide. So there are two methods for the esterification of carboxylic acid. Of course, this is another esterification reaction, but esterification reaction of an acid chloride or an acid halide in general. So that's the second useful reaction of acid chlorides. The other reaction is transforming acid chlorides into amides, the other carboxylic acid derivative, which is next in the reactivity scale, as you remember. So we can take an acid chloride therefore. If we want an amide, of course, we need a source of NR2 in general, so it should be an amine. So if you take an acid chloride, you react it with an amine whose general structure is something like that, HNR2, that's an amine. Of course, nitrogen makes 3 bonds. Nitrogen is in group 5A. It needs 3 electrons to complete the octet. That's exactly why it makes 3 bonds, okay? So this is an amine. If you take an acid chloride, you react with an amine, you form the corresponding amide. But what's also interesting and important also is we need 2 equivalents of the amine, as we will see when we work out a mechanism for this reaction. 2 equivalents of the amine is required to react with the acid chloride in order to make the corresponding amide. So this is the general structure for the amide. So that's an amide. Another useful reaction of acid halides in general, exemplified, of course, by this acid chloride. So therefore, we can make all carboxylic acid derivatives from acid chlorides or acid halides. That's simply because acid halides are the most reactive. The chloride ion is the best leaving group, and of course, because of the other factor, which is the nucleophilicity of the respective nucleophiles. The carboxylate ion, of course, if you want to make an acid anhydride, alcohols and amines, if you want to make esters and amides respectively. So acid chlorides can be transformed into acid anhydrides, which is less than them in the reactivity scale in nucleophilic acyl substitution reactions. We can also transform acid chlorides into esters, and also we can transform them into amides. Now, there are other important reactions of acid chlorides. For example, if you treat or if an acid chloride is treated with a Grignard, and of course Grignards are nucleophilic, not only, of course, as we learned before, not only they are nucleophilic, they are also basic. So if the acid chloride is treated with a Grignard reagent, what's actually formed is the corresponding tertiary alcohol. So the Grignard will attack this carbon, of course, in the acid chloride, initially forming a ketone, but the ketone being electrophilic, it will undergo nucleophilic addition with the Grignard. The Grignard will continue to attack the ketone to form a final tertiary alcohol product. So if the acid chloride, therefore, is treated with a Grignard reagent whose general structure is this, R MgX in general, that's a Grignard reagent in step number 1, and in step number 2, protonation of the resultant alkoxide. What's formed actually is the corresponding tertiary alcohol. So that's the structure or the general structure of tertiary alcohol. So tertiary alcohols can also be made from acid chlorides. That's when the acid chloride is treated with a Grignard reagent. Acid chlorides can also be transformed into primary alcohols if they are reduced with a strong reducing agent such as lithium aluminum hydride. So we can show this in general. If you treat an acid chloride with hydride source, hydride ion source initially, and of course there are differences in the strength, of course, in reducing agents such as lithium aluminum hydride, sodium borohydride, dibal, and others. The intermediate that's initially formed is actually an aldehyde, so the hydride ion will come and attack, of course, the acid chloride. It will do nucleophilic acyl substitution on it to make an aldehyde initially, whose structure is this. But of course, aldehydes are very reactive. They are vulnerable to reduction. They can be reduced, especially if the reducing agent is lithium aluminum hydride. And of course, if aldehydes are reduced, the final product is actually a primary alcohol. So another hydride ion source, if you like, or another mole of the hydride, followed by protonation. So we can write then H3O plus, because then the alkoxide that's formed gets protonated. The final product is a primary alcohol whose general structure is this. So this is a primary alcohol. So primary alcohols can be made from acid chlorides if the acid chloride is treated with a strong reducing agent such as lithium aluminum hydride via the intermediate aldehyde. So we can make primary alcohols, therefore we can make tertiary alcohols. What's also interesting is we can actually transform acid chlorides into ketones with more carbons. That's when the acid chlorides are treated with mild nucleophiles or mild organometallic, such as a cuprate or Gilman type reagent. So if the acid chloride is treated with R2CuLi, so that's the cuprate, the Gilman type reagent, being a mild nucleophile, it will only do a nucleophilic initial nucleophilic acyl substitution reaction on the acid chloride. The ketone that's formed, okay, will be the final product because the cuprate is not strong enough to attack that ketone, as we have seen in the Grignard reaction before. So the final product would be a ketone, interestingly. So a ketone can be made from acid chlorides. That's if the acid chloride is treated with a cuprate, being a mild or a nucleophile or a mild organometallic. So this should be a very, very useful transformation. And of course, if you note, the number of carbons in this ketone should actually be more. And of course, that increase in the number of carbons, or that extra carbons, or those extra carbons should come from the cuprate. So that's another useful reaction. The last reaction which we should discuss, but although it should be obvious, is actually hydrolysis of the acid chloride. Acid chlorides, being very, very reactive, can undergo easy hydrolysis to the corresponding carboxylic acid if the acid chloride is treated with simply water. You don't even need an acid or a base catalyst. So if the acid chloride is treated with water, they undergo hydrolysis to the original carboxylic acid from which they came, if you like. Okay, this should be also a very fast reaction because acid chlorides are very, very reactive. Again, that's because of the excellent leaving group ability of the chloride ion. Actually, if you leave a bottle of an acid chloride for a long period of time, it can undergo hydrolysis easily. So this is another reaction of acid chloride. So in summary of this scheme, acid chlorides are very versatile because it is possible to make from them acid anhydrides if the acid chloride is treated with a carboxylate ion, or acid chlorides can be transformed into esters if the acid chloride is treated with an alcohol in the presence of a base such as pyridine. Acid chlorides can also be transformed into amides if the acid chloride is treated with an amine. And remember, we need two equivalents of the amine, as we will see in the mechanism in due course later on. Acid chlorides can undergo also reactions with other organometallics such as the Grignard, and if they do, a tertiary alcohol is formed. If they are reacted with a strong reductant or reducing agent such as lithium aluminum hydride, the corresponding primary alcohol is formed. If the acid chloride is treated with a cuprate or a Gilman type reagent, an interesting or a very useful ketone product is also formed. A simple reaction is hydrolysis of the acid chloride to give the corresponding carboxylic acid. In summary of this, acid chlorides are very versatile and thus very useful organic compounds.